Hey everyone, welcome to the first video from section 3.8. So in this section we're going back to more physical applications, and this time we're doing physical applications of non-homogeneous second order equations. So we talked about mass on a spring in section 3.7, now we're going to talk about forced masses on springs in section 3.8. So let's go ahead and jump into it and see what I'm talking about with this stuff. So we're talking about here what are called forced oscillators. So by forced, we basically just mean that there is an external force in the system, external force, which in terms of ODE terms means this is a non-homogeneous equation. And hey, we just spent the last two sections talking about how to solve non-homogeneous equations. So let's see how that works and what kind of physical phenomena we can get from solving these equations. So what this means, we're looking at an equation of the form mu double prime plus gamma u prime plus ku equals f of t. We're going to assume we have constant coefficients again like our mass on spring system, but now we have an f of t on the right-hand side. And in general, we'll talk about this more in the next section, we're going to assume that the forcing function is an oscillatory forcing function. So it's a cosine function, more or less. Now, how did we solve non-homogeneous equations? Well, we either could use undetermined coefficients, which is going to be nice here with the cosine function, or variation of parameters. In either case, we know what the solution is going to look like. So by how we solve non-homogeneous equations, we know that u of t, the answer, is going to be c1 u1 of t plus c2 u2 of t plus some function capital U of t, where these guys here solve the homogeneous problem, and this guy solves the non-homogeneous problem, right? That's what we get. We get the homogeneous part plus whatever particular solution we find to solve the non-homogeneous part. Now, when I was talking in section 3.7, we talked about what these functions u1 and u2 look like. We got explicit forms for all of them, and there was one key point that we mentioned about these solutions, no matter what the damping was, no matter what anything was, as long as there was damping. If there's no damping, then this doesn't happen. As long as there is some damping, we have this fact. So as long as gamma is bigger than 0, so gamma not 0, then the discussion in section 3.7 said that u1 of t and u2 of t go to 0 as t goes to infinity. So it doesn't matter what gamma is. As long as it's not 0, then my two solutions to my homogeneous equation will go to 0 as time goes on, because they were either a sum of complex exponentials of real valued exponentials of both negative coefficients in front. They were a complex valued thing where the real part was negative, or they were a plus bt, repeated root case, times exponentials, but that also had negative power in it. So in any case, as time gets longer and longer, this is going to 0. So as time goes on, the C1 U1 plus C2 U2 term is going to kind of vanish. It's going to go away. And we're just going to be left with the U2, the U of T term, the capital U, as our solution at long times. So for this reason, we call the C1 U1 plus C2 U2 part the transient solution, because it vanishes as t gets large, and really because it's an exponential into how it decays, it's generally not important after a few seconds. So it doesn't really take that long for the solution not to matter anymore. And then all that's left is our capital U. And we call this the steady state solution, or the forced response. So this is sort of how the system in general will respond to this forcing over time, not determining on where it starts or anything. It's going to end up in this sort of cycle no matter where we start, because C1 and C2 are different by initial conditions. So what this really says is, in the long run, the initial conditions don't really matter all that much. They matter a little bit in terms of like maybe a shift a little bit, but they don't matter too much in terms of the final answer, because the C1 and C2 that came from initial conditions, those terms all vanish as time goes to infinity. So eventually, it doesn't matter where we start or what we do, the forcing takes over and forces, it's a force, forces the spring and mass to do a certain thing as time goes on, because the original conditions don't matter anymore. All right, so I just wanted to kind of set up those terms here in this video for the idea of what we're going to be talking about in the next couple sections. So in the next couple of videos, what we're talking about is what these solutions actually look like, how they come together, and what sort of weird things can happen for different values of damping coefficient and the forcing. So a lot of the stuff in this video is going to be sort of shown in Maple just because the calculations get kind of nasty. But if you see things with an exam, you should either be able to A, answer a conceptual question about it, so when does a certain thing happen, or B, do the calculations in a very easy case. All right, so that's it for this video. Thanks a lot for watching, and I will see you in the next one when we start doing some examples.